So chapter 2 was all about limits. But if you recall, at the beginning of chapter 2, we introduced a motivation for studying limits. So one of the examples we looked at at the beginning of chapter 2 had to do with average velocity and instantaneous velocity. So let's recall what average velocity is. Average velocity is just the change in distance over change in time, but we need a time interval, right? We can calculate the average velocity over a finite time span, right? From t equals, say, 2 to t equals 3. We can calculate the average velocity. But we also introduced the concept of instantaneous velocity. So the instantaneous velocity at a point in time, right? So at, say, t equals 2, right? And in order to find that instantaneous velocity, we need to find the average velocity and over shorter and shorter time intervals. So if we want the instantaneous velocity at t equals some value a, right, we can take the limit as t approaches a of the average velocity, right? Now you can see what happens. You can see this formula here for instantaneous velocity. Now if t approaches a, the denominator looks like it's going to go to 0, right? So it looks like it would be undefined at a. But now that we understand limits, we can sneak up on it. And that's what we're going to do here. We're going to use limits to solve this problem, which is really the same. It's a very similar example to what we already did at the beginning of chapter 2. All right. So you might even remember this one. We have a watermelon that is dropped from the roof of a building that's 125 meters tall, and the height of the watermelon from the ground is given by this function s of t, right? 125 minus 5t squared. All right. Our first task is just to find s at 2, right? We're trying to find the height of the watermelon after 2 seconds. All right. So we're gonna put the value 2 into the equation and calculate it, right? So 125 minus 5 times 2 squared, so 5 times 4. So we get 125 minus 20, which is 105, right? 105. Now the units are meters, right? Because the distance is being measured in meters. And it says interpret its meaning, right? So this is essentially saying that after 2 seconds after being dropped, right? So I'm just going to say after 2 seconds, the watermelon is it's 105 meters above the ground. Okay, that's the interpretation of that s of 2 equals 105. Okay, that's what it means. All right, so the next question is asking us to find the average velocity over this time interval. Okay, we've done that before. So I'm going to call it v average, right? Because that's what we used up above. All right, so it's going to be s at 4 minus s at 2 all over 4 minus 2. Okay, so we need to calculate s at 4. Okay, 125 minus 5 times 16. All right, so I'm going to put that in my calculator, and I got 45. So basically that 45 is just saying that at t equals 4, the watermelon is 45 meters above the ground. At t equals 2, it was 105, so that'll give us our change in distance. And then 4 minus 2, well, that's just 2. Okay, so what do we get? I put that in my calculator, and I get a negative 30 meters per second. All right, it's meters per second now because it's a velocity, right? That's telling us how quickly we're covering distance over that. That's the average, right? That's the average velocity over that time interval from 2 to 4. All right, so the next thing we're going to do here is calculate average velocity, but instead of from 2 to 4, we're going to do find the average velocity between 2 and some arbitrary value t. All right, but it's the same process. So I'm just going to say the velocity is equal to s of t now, right? Instead of s of 4, I'm just going to put in s of t minus s at 2 all over t minus 2, right? It's the same equation we had before. It's the average velocity. I could even put AV right there. Only now we're just using an arbitrary value t so that we can use a limit, right? Now, let's calculate what that is. What do we got? So we're going to have, let's see, I think I can have room here. 125 minus 5t squared, right? That's our formula. And we know s of 2, right? We calculated that value was 105. And then just over t minus 2. So let's take one more step and combine those constants. So I'll get 20 minus 5 t squared over t minus 2. All right. So there's our average velocity between t equals 2 and some arbitrary value t. And our next step is to use a limit. We're going to use a limit to find the instantaneous velocity at 2 seconds, right? So, oops, what happened there? All right, so now we're going to take the limit, right? So actually, let's write it this way. Let's go ahead and write it out. V instantaneous, V inst is equal to the limit as t approaches, our a value is 2, right? We're trying to find the instantaneous velocity at 2. So as t approaches 2, of this, I'll just go ahead and write 20 minus 5t squared over t minus 2. All right. Now, as t goes to 2, right, the denominator goes to 0. So this, it's undefined at 2, but we're going to sneak up on it. All right, so we need to see if we can simplify this expression somehow. So I'm going to factor the numerator. And I think what I'm going to do is I'm going to factor out a -5 just because I like my quadratics to have a positive leading coefficient, right? If I factor out a -5, then I'm going to put the t squared first. T squared minus 4, right? That's the same thing. And the denominator is still t minus 2. But you can see what we can do now, right? Whoops. You know what I forgot? Don't forget this. Let's see here. Let's see. I'm gonna shift this over because I forgot to write the limit, and I gotta write the limit here because this is still, we haven't actually taken the limit yet. So I'm gonna make some room here, and I'm gonna write the limit as t approaches 2. I gotta carry that along until I actually take the limit. All right. It's easy to forget to do that. All right. So the next step, I got to carry along the limit. Limit as t approaches 2. And I'm going to go ahead and factor that difference of 2 squares. So that's going to be t plus 2 times t minus 2. And then you can see where we're going here because the t minus 2, we have a factor of t minus 2 in the denominator and in the numerator. And as long as we're not going directly to 2, right, as long as t is not equal to 2, I can do that. I can cancel those factors. All right, so let's see what we got left. The limit as t approaches 2, and what we have left is a -5 times t plus 2. All right. Now, we don't have any problem with just directly substituting the 2 in. And so that limit will be -5 times 2 plus 2, which is 4. So that will give us a -20. All right. And the units, again, are still meters per second. All right. So now if you remember back in the beginning of chapter 2, what we did was we just took values that got closer and closer and closer. We looked at average velocity between 2 and 2.1, and 2 and 2.01, and 2 and 2.001. Okay. So, but now we don't have to do that. We can go directly to the answer by using a limit. And so our answer is a -20 meters per second. All right. So I'll meet you. This video is long enough now. So I'll meet you in the next video.